Hello, everyone. Welcome to MACSMIN 2024. It's a great pleasure to introduce Professor John Helliwell from the University of Manchester, who will talk about his recent book entitled The Scientific Truth, the Whole Truth, and Nothing But the Truth. Over to you, John, please.
Thank you, Vitaly. And it's a real pleasure to be able to speak to this week-long symposium. And I apologize not to be there in person. My wife and I are doing house viewings in Plymouth where we're planning a move. So I'm a bit constrained domestically. Anyway, here we are through the wonders of technology. In addition to my new book, and I don't know if I'm on video. Anyway, here it is in the flesh. I'm very stimulated by a US National Academy of Sciences and Engineering report, Reproducibility and Replicability in Science, which I commend to you as really excellent, 2019. So I advertise that here on this opening slide. My talk is actually very general, and I've been representing IUCr at UNESCO in the last 18 months on its open science initiative. And that's led me also into the International Science Council deliberations, where I've been making inputs for them on open science and also publishing science. And basically, in the top point here in the contents, there is a massive thrust on open science from governments, organizations, and funding agencies. And obviously, the front cover of my book, the center word in the infographic, top left here, I'll just get a laser pointer. The top left here, the key word for me is in what we do is trust. And puzzlingly, in these different Zoom events, and there's a lot of them that UNESCO in particular has organized, trust isn't emphasized. And of course, crystallography community, we have a tradition over many decades of peer review of articles with underpinning data. And exemplars in the general checks is the IUCr's Checkcif for chemical crystallography and the PDB's validation report. Now, the question arises, once the editor and their referees and database validator are content with an article and the underpinning data, what are the standard uncertainties on atomic coordinates and atomic displacement parameters? Now, after his retirement, Durward Cruikshank, who made 60 years of contribution on this topic, challenged me about how the protein crystallography community didn't have standard uncertainties on atomic coordinates and atomic displacement parameters. And I'll go into that later. The core point about digital data archiving, it's expanded enormously and it allows raw data preservation. So we get very close to the objectivity that we seek in science. We don't get there completely. And then if we think in parallel to what happens in the law, as my publisher lady for my new book pointed out to me, if we have in law the truth, the whole truth, and nothing but the truth, then why not in science as well? And so my book title became that because I'd submitted it with a simpler one, The Truth Scientific. Anyway, we now have this longer title of my new book. So, point one, this open science thrust from these organizations and so on. So the UNESCO list of things here, and the web link is at the bottom there. And in bold, we have transparency, scrutiny, critique, and reproducibility, equality of opportunities, responsibility, respect, and accountability, collaboration, participation and inclusion, flexibility and sustainability. I think we call these in US speak motherhood and apple pie type terminologies, and how could we sort of disagree with them? But the top one, scrutiny and critique, I don't think necessarily goes with open science in the way that they define it. And I'll dissect that aspect in particular. So the International Science Council work on open science is very thorough. And so we have two documents at left here, which they label as problems, and two documents at right, which they label as solutions to those problems. So in terms of problems, they are very exercised by the business models of the publishing sector, and the way in which that works, fault is found, and they wish to make scholarly publishing work for science in the digital era. And with that, they think they will strengthen research integrity, and of course raw data being fair is part of that, but fair doesn't equal open, and I'll analyze that as well. Now, the thing that really worries me is what they call the normalization of preprints. And in that is the doing away with trusted publications altogether. And I think that is a real error on the part of the International Science Council. So the ISC details these things, and I put a couple of the points there, my worries and comments. So in terms of normalization of preprints, I think for that you would have a really haphazard peer review versus a thorough peer review within a trusted publication. And so that links with this comment that they make of reforming the journal concept. But I ask, why reform? The scientist as customer can make better choices via the market. And as a scientist with a big enthusiasm for the International Union of Crystallography and its journals, I'm always exercising my customer choice, because I know that they make only a small surplus, not a big profit. And what surplus they do make is ploughed into the community anyway. So that power of customer choice, I think, is very important. Now, the view of the European Union is interesting, and they call it the 8 pillars of open science. And so we have them from left to right: rewards and incentives, next generation metrics. They don't like the impact factor, for example. The future of scholarly communication. The European Open Science Cloud is at the pivot of the center of their ideas, and that's a very important initiative. Then you have fair data, research integrity, skills and education, and citizen science. But the European Open Science Cloud, which as a temporary measure, it means Zenodo, based at CERN in Geneva. And I find Zenodo very powerful for all sorts of things, of preserving my talks, preserving raw data, and so on. So as I say, trust isn't emphasized, and trusted journals in particular. And I come back to this crystallography global community view that peer review of articles with underpinning data is essential. And you see on my front cover in this infographic, I brought in the US National Academy of Sciences words, reliability, reproducibility and replicability. Then I've also introduced a link to our R factor in crystallography, which is interpreted a lot of the time as reliability, although in fact, looking back at the historical record, Arthur Wilson, Derwig Cruikshank, they refer to it often as a statistical residual. Then we have, of course, the fair. So data should be findable, accessible, interoperable, and reusable. And so the reusability word comes out. And then fact is from social sciences. And so fact is an acronym meaning fair. So data may be true, but you have to be fair to the individual. They bring in the A for accuracy, which is not present in fair. C is confidential, which is sort of obvious for social sciences, and T is for transparency. So there's an evolution of words here in the past decade, which I find really rather interesting. Now, in crystallography, to delve deeper into what we do, we've had this long-term effort on the crystallographic information framework, and that's needed for data transmission and exchange. And the crystallographic information file brought in by Sid Hall and colleagues, Sid Hall in Perth, Australia, and won the 2014 Co-Data Prize. This allows for us to do data consistency checking with Checkcif, and that was initially coordinates, and then as the archive expanded to structure factors, extended to those as well. And the IUCr, we have a whole committee that's dedicated to the maintenance of the CIV standard, and that's chaired by James Hester in Australia. Now, in 2003, the PDB validation started. We keenly supported that. I was editor-in-chief of ACT-CRIST at the time, and the validation report term was introduced from 2010 onwards. So all this is about provenance and trust your data, know your data, share your data. And what does that mean for the FAIR principles to have practical effect? There must be trust in the crystallographer, their articles, their entries in the database, their data sets. Trust in the process of crystal structure analysis, and that means proper recording of metadata for the experiment, the processing and the deriving of the model workflows. And then trust in the measurement at source is the new opportunity that the expanded digital archives have given us to extend to raw data. If we have reproducibility of a given study, then others can design their own experiments to see if they can replicate the phenomenon that the first investigators exposed. So that is the gist of it. In terms of a survey of databases, I offer you this reference that came from the International Data Week in Denver in 2016, and Brian McMahon and I organised a session for the most popular databases and crystallography and databases in Data Science Journal. The reference is there. So we have a coherent framework that has evolved. And so from left to right, this is a very complicated diagram, and I'll only bring out some of the points. But we have our probes of the structure of matter at the left here. There's three options: the X-ray, the neutron, and the electron. Our crystal, of course, and an appropriate detector. And then we measure at a central facility or the home lab. And so when we commit to those measurements, we've picked the sample we like, then that is a moment where, if we can record it, it's a historical version of record, an important moment in our process. We reduce our data, and we have many options for the processing software, which is the first interesting point I'll bring out later. And then different options for the model refinement, and then we pick our journals, so the customer choice moment, and we have our appropriate databases for chemistry and biology there. And then there's these shapes of what you might retain as the scientist: archive at the facility, deposit, publish, and validate. Excuse me. So as I say, it's rather complicated, this, and I do invite you to study the shapes and the colours and the flow. Now we have a truly excellent range of opportunities as researchers for linking all our underpinning data to publication, raw, process and derived data. And for Exemplars, we can mention Protein Data Bank Japan has launched its raw data archive a few years ago. We've got proteindifraction.org, a leading raw data archive in the US, along with SB Data Grid. In Uppsala, we have the Coherent X-ray Imaging Database, which extends to serial crystallography. And the cryo-EM people are also very active on making available microscopy density maps, electrostatic potential maps, and of course we have the PDB accommodates those structures as well as the crystal structures. Now the CCDC lost its funding in the Mrs. Thatcher era, who argued that if it was needed it would self-finance, and so they're a charity and not for profit. But in the open science era, the crystallography open database has started here, and here's its logo, COD. And basically their argument was that from the CCDC, you couldn't download the whole database at once, which you can, of course, for the PDB. And so they started web trawling to create entries for the COD, and people also deposit directly there as well. So we have something like 1.2 million chemical crystal structures in the CCDC and about 500,000 in the COD. Brian McMahon stressed to me the business advantage of these two, which might be seen as competitive, because duplication is good business practice. So if there was a fire, let's say, at one, then you've always got the other. And then, of course, we've got the EU effort with Zenodo, which I've mentioned already. So let's come to the Cruikshank challenge to the field of protein crystallography. What about individual atomic coordinate and ADP error estimates? So Cruikshank, he posed this challenge to me. We just entertained Judith Howard to her lecture in Manchester, and over lunch he said, why do you protein crystallographers not have these error estimates? And I said, oh yes, well we do. We have the Lusati estimates overall at the end of the refinement of our model. And he said firmly, that is not an indicator of precision. It's the distance you are from convergence. So in this paper, which is very detailed, and I commend it to you, he first of all takes apart the notion that the Lusati estimate is appropriate at all. So he derived this overall formula, the diffraction precision index. And so we have for coordinate X and for an average B factor atom, we have the terms on the right. So Ni is the number of atoms of type I, P is the number of observations minus number of parameters, C is the data completeness, R is the R factor. Note he uses the term residual and not reliability, and D-min is the resolution limit. In that paper, he also indicates that it can be extended to an individual atom, and the appropriate formula there, dpi overall multiplied by B atom divided by B average square root for consistency of units. And we, my colleagues in Bangalore and myself, we've extended to the individual atom, and we can thereby assess if an atom shift is significant or not. And this is particularly interesting for structural dynamics. In this simple example, we're comparing two different crystals, and there is a apparent shift of the histidine here. But in fact, it's only at the 2 sigma level in terms of the Cruikshank DPI, and therefore we could rule it out as significant in a time-resolved structural dynamics if we extend to that. So the Bangalore bioinformatics group, led by Professor Sikar, we introduced this online DPI website where you can look up a PDB file, and you get the new column added at the end here for the atomic coordinate error. 7CCY is particularly interesting. It's held at the PDB-J. It has its raw data available, and it's one of these where there are no peaks in the FO minus FC map in COOT, which is the well-known molecular graphics program that appears in its default search. So it's a model that is, if you will, complete in that sense. Now, what about the B factors, the atomic displacement parameters? So with my colleague Loes Groen-Battenberg in Utrecht University, this indicates using several different processing programs on individual crystal raw diffraction images. And we have 11 different crystals here, and we have the Wilson B minus the Revine model B, and the data set number on the x-axis here. And you see that there's really quite a spread of what we find out from the same diffraction images with the different programs. And so this gives us an idea of the precision of the B factor. And if we look at what's sort of reported in our papers, this is from an IUCr journal, and I've taken off the clues to who it is, but we get quoted in the table here, the so-called table 1, although in this case, in this paper, it's table 4, to 2 decimal places and 1 decimal place. Well, that's clearly inappropriate and false precision. It should really only be quoted to integer level. Now, precision is not the same as accuracy. Accuracy must involve 2 or more experimental methods. Each one, of course, we try to minimize its systematic errors and minimize its random errors. But the different methods then have the advantage of their different random and systematic errors, and gives us this opportunity to compare the outcomes of 2 different methods to determine how close to the truth we are. And of course, we never know the truth. So that's a big challenge, but that's the way it is. Now, if we compare NMR in a solution protein structure determination, and if you look at ACT F in the early 2010s, we see quite an effort by the then editors, Howard Einspar and Mitchell Gus, to accommodate NMR structures in ACT F as well as protein crystal structures. And that in turn gave them an opportunity to compare results on the same one. So in this, taken from this paper, we see the NMR ensemble. There's a familiar way that the NMR spectroscopists analyze their data. And then in firm black, we get the crystal structure. And it's pleasing to see how well they agree. So we could say to ourselves, we are really close to the truth from our 2 methods. But the interesting bit really is at top left here, the R149, where the NMR is showing a big spread. And in fact, the electron density in the X-ray would not be visible because it's too smeared out. So there we get a much better indicator of truth from the NMR than we do from the X-ray crystallography. Anyway, there's a whole set of articles in ACT-F 2010, and I commend them to you. Now, the raw data opportunity, let's look at that. And for those that don't know crystallography, and obviously I've got some highly expert people on the line here, so they'll have to forgive me for going to this basic level. So we have our raw data image, and thousands of these make up our data set. This is just a typical example. We process the individual diffraction spot intensities, and we get our typical file here, and from that we make our model. This is a chemical crystallography model, so we do see in brackets here the estimated standard deviations, now called standard uncertainties, on these particular distances. And each step of this includes metadata, which of course are also data, and we need complete metadata in order to know what the workflow really was. So if we look at this from data science, they have this data pyramid, and we have the raw data here, and they use term like ground truth, and our processed and derived model. And of course, as we come close down to the raw data, then we're getting objectivity, whereas the narrative is really rather subjective. Now, of course, an instrument diffractometer must be calibrated by a person, and this leaves some degree of subjectivity. And of course, a person picks a particular protein or sample, so that is another element of subjectivity. And I've just picked this infographic here from the web, which shows the evolution of technologies, cards, tapes, and so on, up to the cloud now, where we have this massive expansion of digital data storage capability. And crystallographers, like the astronomers and the particle physicists, have always been at the forefront of harnessing new technology as it's come about. Now, what opportunities do these give us? Well, we can analyze the data at higher resolution than used by the original authors. We can improve our methods because we can set benchmarks. We can check the interpretation of the symmetries of the crystal. But here there's an initiative led by Randy Reed to have unmerged process diffraction data, and that allows the checking of the symmetry in a more economic way of the data storage than the whole raw data. Now, to continue, however, to the advantages of the raw data preservation, analyzing from diffraction image for multiple lattices is obviously possible, and the diffuse scattering reflecting the correlated motion or disorder of atoms in the crystal is also then available. And a range of case studies available in this article here. So the raw data provides the opportunity for the person looking at the work to analyze through their own eyes and not the lens of someone else, to use a metaphor. So we get a better understanding what we do experimentally. We can harness new methods and software, enable new science, and understand the subjective choices made in data processing. And Vladek Miner in particular has published very nice work on showing the different impact of subjective choices that are made by the protein crystallography community. Now, these are in addition to the decades-long benefits of archiving coordinates, which allows us to analyze structure and bonding trends, get snapshots of conformational dynamics. People such as Hans-Piet Berge in Switzerland have led the way on that. And the process diffraction data, when that could be archived, then of course you can refine a structure based on the author's structure factors. Now, how to organize this opportunity of raw data archiving possibilities. So at IUCr, we thought that it ought to be a part of IUCr data, and we launched raw data letters. And we have several of these already. Here's one that Lois Kroon-Battenberger's main editor put into the journal. It shows a structure that was already published, but it shows the diffraction images. And in fact, there were new opportunities there because of twinning and diffuse scattering for further analysis. And we developed, led by James Hester in Australia, chairman of the ComSIFs, a Checkcif for raw data. And you see here the various automatic checking, each item is showing pass. And from that, we can, with the help of the author's submission, we can create a raw data table of key details. Now, we've had rather few of these, and we've been putting out a lot of publicity at our meetings. And so at the moment, we can say, well, then this opportunity is not so popular. Now, are all areas of crystallography and diffraction the same in what they perceive as their raw data archiving needs? Now, the Commission on Biological Macromolecules, chaired by Vladek Miner, has enthusiastically led the way for, and I've helped with that as former chairman of the Committee on Data. So we're seeing the notes for authors now that any data processing methods and new structures papers must have the raw data DOI cited. The chemical crystallographers have been very thorough as well, and they organised a workshop linked to the Prague Congress, and they had a title for the workshop, "When should small molecule crystallographers publish their raw data?" And the answer from that and a questionnaire in the IUCr newsletter was in special cases. So if the diffraction pattern is particularly challenging and therefore challenging to the current software, then yes, it's obviously worth preserving the raw data. Powder diffraction, the paper by Miguel Aranda, who at the time was ALBA science director, the Spanish synchrotron, set out a number of ideas for how raw data might be useful for powder diffraction, and the Commission on Powder Diffraction is looking at that. It's now quite a while that they've been looking at it. Suffice to say, though, that the International Centre for Diffraction Data, the ICDD, do accommodate raw data, and they have about, when I last checked, 10,000 examples. But their definition of raw data isn't the 2D image, it's where they've not subtracted the background from the 1D profile. So you have to be a little bit careful about what people are talking about for a given raw data set. Now, Europe's facilities, synchrotron and neutron, have been very active. And so, for example, Diamond Light Source, ESRF and Soleil have saved all their measured data since they came online, and have a policy of commitment to release of all raw data after 3 years. And from 2018, ESRF even get a DOI per proposal. And users can provide additions to that as well. And then in Germany and UK, we have the national projects, Daphne for NFDI in Germany and the PSDI in UK. And they're looking at a coordination of fair data opportunities, including raw data. And I've mentioned the Open Science Cloud already. PANOSC is the photon and neutron open science cloud, which is linked to the EOSC. So here's an example of an infographic from Daphne for NFDI, provided to me by Bridget Murphy. And so they envisage all the way from proposal round this, going clockwise here, to publish. And the data moment here, after an embargo period, is released anyway, whether there's a paper or not. Now, I don't think this is necessarily a good idea. I think there needs to be more power remaining in the hand of the PI to decide when there should be the release of the raw data. Now, at DAISY, Edgar Weckert, when he lectures on this, the director there, I think he's just retired, he does stress that the PI can appeal on an annual basis for raw data not to be made available yet. So, open science is a grand principle. I pose it as a question. What is the grand principle? All measured data, including even unpublished raw data with no derived molecular structure model, should be made open. Now, there's certainly useful examples. So the ESRF Paleontology Initiative is interesting. There, researchers in Europe agreed that they cannot analyze all the data unless they make it open to a global set of experts. Then you have, for example, the Diamond Light Source COVID Research Initiative, and they automatically, Graham Winter there, copied raw data sets to Zenodo. Now, we do hit limits of what the capacity is because the Dectris detectors are getting ever more fast and even bigger volumes per data frame. And so the obviously things like unuseful experimental data have to be deleted. such as empty data frames as a sort of trivial example. But I do emphasize that I think it's still a gray area for me, where you have a useful, potentially useful raw data set that the automatic release when there's no publication is not really clear to me as a reason for doing it. So with the data rates, there are interesting at-facility analysis procedures. So PANOSC has VISA, developed at the ILL, and CCP4 has got IMOS film through the cloud. So this obviously keeps everything near to where the data were measured. And if we come to conclusions, and I've got some open question slides before I finish off. Fair, of course, does not necessarily mean open. So the CSD at CCDC has been fair since 1965, but in the way I described is not open because you can't download the whole thing. Secondly, trust in a discovery needs reproducibility of a study, especially its data analysis procedures. And with that, others can design their own experiment. You've got to have peer review. And so the replacing all journals by preprints, I think, is a big error of judgment of the International Science Council. I've stressed the raw data benefits. Community agreed crystallographic standards are vital. Getting what means community agreement is interesting in terms of, say, the Cruikshank challenge to me. Now, industry, I'm going to come to in a moment. Let's just touch first on open software. So that means the source code. So CCP4 is open source. You can check any calculation you like made within CCP4. The processing system XDS is not open source, but very popular. And the steward of the software, Kai Diedrichs, is very responsive on the CCP4 bulletin board, answering any queries. So is this then an alternative to open source for ensuring reproducibility? I think it could be argued that it is. Now, molecular graphics software, free for academic use, are CCP-MG and Chimera X, but PyMol, by contrast, is free for educational use, but not free for research or publication, i.e. even by academics doing non-commercial work. So this is complicated, isn't it? Now, what about industry? Industry provides our products, and you can work as a customer to pick a product. You exercise your choice. Now, industry does cooperate. We have pre-competitive phase, and that allows opportunities for open science. And infrastructure can be shared, such as the Industrial Macromolecular Crystallography Association, CAT, the Collaborative Access Team at the APS. They have developed a beamline led by Lisa Keith, which that they all use. But industry's research is very successful, and I think, you know, it requires its privacy to be respected, and therefore not open. And UNESCO and the ISC have not analysed this at all. And I've made myself a bit of a nuisance at the Zoom meetings that they've hosted, pressing this point. Now, so industry doesn't take an interest in all the important problems. So neglected tropical diseases, for example, you know, nobody can afford to pay for medicines that industry might develop. So I think there's a great opportunity there for open science and the academic community to link together to make progress. And indeed, there is a coordinating effort, and it involves people like the World Health Organization for doing that sort of thing, Gates Foundation and Wellcome Trust for funding. Now, a very interesting case recently on software and industry, let's take both points together, because Google DeepMind published its AlphaFold 3 software results in Nature and got a lot of criticism, and there was a petition to Nature stressing that the source code should be made available. And so Nature was forced into an editorial, my word to use the term forced, and they headed it, "Why did Nature publish AlphaFold 3 without its code?" And a rather interesting part of this is we think that research, regardless of the sector that does it, should be evaluated through peer review and published for the benefit of society and science. But on top of that, they also say the private sector funds most global research and development, and those results should be published in peer review journals, and they therefore offer the view that they need to be flexible about how much of an article is made open, in this case, the software. So this is a very interesting editorial, which I commend you to look at as well. Now, what about open education? So we see this emergence of MOOCs, massive open online courses in crystallography in particular, as well as many other things. And so from Rigaku, the company, we have their single crystal e-learning course, have been very popular. And then from GIVSERIVET and the Soleil Synchrotron, we have this initiative led by Marie-Hélène Ledoux. From Lausanne, the EPFL, there's a MOOC on synchrotrons and X-ray free electron lasers. And so these initiatives, of which we're included, I think they are very interesting in terms of impact of open science. The Centre for Open Science in Charlottesville offers a new framework, and they have a 14-minute video, which very briefly and very successfully makes the case for some radical changes, but with a different emphasis to the UNESCO and the ISC. They don't, for example, report a plan to replace everything by preprints. Instead, they offer these ideas, which I think have got interest to us. Pre-registration of studies. This is to avoid making hypothesis after you've found out your results. It's a thing more for the neurosciences and social sciences. And then perhaps more important for us is we could do more on reporting negative results. Publishers and our articles emphasize positive outcomes, and to think more about what we might do in making open our negative results. I think we could make a useful step forward. So that's the end of my presentation. I'm within time. The members of the IUCr Diffraction Data Deposition Working Group and the current members of the IUCr Committee on Data have been very valued colleagues. And on the open science, Andrew Allen, Editor-in-Chief currently of IUCr Journals, and Peter Strickland, the Managing Editor, asked me to do the work attending all their UNESCO and ISC Zoom events, and there was a lot of them, each one 2 hours at a time. The Co-Data Data Policy Committee was very helpful, because as I was stressing the needing a better role for the PI in when raw data is released, the question came up in my mind: who owns raw data? Is it the facility in the home lab? Is it the chemical synthesis PI, and the diffractometer person is not holding the ownership card? So they gave us guidance, which had a very useful, simple principle, common sense. Before anything is measured, agree what the sharing plan is. Now, finally, the Checkcif for Raw Data project team, led by James Hester, showed you the example from raw data letters there. We see as having great potential for both published data and unpublished data. And Fabio Dal Antonio at the EuroXFEL in Hamburg there, and Andy Gertz, they've been very active in this EU project OSCARs, so making open data a reality. And so Fabio led one of those projects, and that one has been awarded. We're just waiting for the announcement of which is the list of funded projects. But the EU OSCARs website is active, and you can look up what themes of open data were funded in the recent round, which was the first round, and more rounds of funding are anticipated. So with that, I thank you for your attention. I acknowledge the University of Manchester, and of course I spent many decades involved at the SRS in Daresbury, which completely shaped my thinking as well with respect to data at the central facility. The US National Academy's report is really fabulous, and I do encourage you to read it. And maybe if you fancy it, I know that Vitaly has read chapters 6, 7, and 8, and so on. So there is my new book. Thank you very much.
Thank you. Thank you, John, for your nice presentation. Yes, please. Thanks, John. And now I'll stop recording so that